Hello and welcome to this fourth APL quest. Check APL Wiki for details. Today's quest is called Keeping Things in Balance. Here we take a character vector and it has parentheses in it. We need to check whether the parentheses are balanced so it looks like a normal mathematical expression, or whether things are wrong. Say we begin with closing parentheses that aren't there, or we end with some open parentheses. Let's get started. Let's start by having a test data just to see how this works. So we create a character vector and let's put in some expression there. For example, something like this. Okay, this is a balanced one. And the approach we're going to start off with today is that we're going to find out where the depth of the parenthesis nesting changes. And there are a few different ways we can do that. Then later we'll move on to actually finding out whether or not the parentheses are balanced or not. A very simple approach, and a classic one in APL, is to convert the input into a normalized form. So we can look up every character in this test case, the indices of its characters in the open paren and closed paren. And APL does this that if an element isn't found in a lookup array, then we get the next index. So 1 and 2 are the open and close, and 3 is any character which wasn't found. Now we need to map these to indicate when the parenthesis level changes. So we use this to index into a vector, and we say when we have an open parenthesis, then we increase the parenthesis level. When we have a closing paren, then we decrease the parenthesis level, and any other character we map to 0 as it doesn't affect the level. Let's stack this together with original input. So we're going to mix the concatenation of the enclosures with the original. And we can see how when we have an open parenthesis, the parenthesis level increases, closing parenthesis decreases, and any other character leaves the parenthesis level unaffected. So we can make this into a function. Let's call this the parenthesis depth changes using indexing. So it's going to take this formula. But there are other ways that we could do this. We can, in a similar manner, but instead of lookup, we can do a comparison. So if we take the character vector consisting of these parentheses and do an outer product with the characters here, we get a table. And we can do the same trick as before to stack up on top. Oops. What happened with... Oh, it's a... Yeah, that's not what I should have done. I increased the rank. We should just stack this up. It's already a matrix. There we go. And we can see here that the first row of this Boolean matrix indicates whenever the parenthesis level increases, and the second row indicates when it decreases. And then the other row is, of course, 0. And then we can do this clever thing that we can subtract the top row from the subtract the bottom row from the top row, so the top row minus the bottom row. That's a vertical minus reduction. And that gives us the same thing. Now we need to stack them on top of each other. There you go. Okay, now we get the same thing as before. So this is a different way of doing it. And we can call this the parenthesis depth changes using the outer product, O for outer product. So we can even do this as a tacit function because it's so simple. And the argument is just the identity right there. Okay, but there are more ways we can do this. We can also do the two comparisons each by themselves. So let's say we take the comparison to the left parenthesis and the comparison with the right parenthesis and put them next to each other. That gives us these two vectors. We could of course stack them on top of each other and then we get just like the outer product. But since we're going to subtract them from each other, we can just put the minus in between. And that gives us the parenthesis depth changes right away. We can give this a name and we can again make it into a tacit function because it's really simple. So we can, it looks very nice as well, symmetric like this. So we can bind this to equal, making equal equals a left parenthesis in a monadic function, and subtract the same thing. We can put the, because equal is commutative, we can put the argument on either side. I'd like to put it like this because it looks really cool. So this is the depth using a fork with the two outer tines, equality to the two parentheses, and then subtracting the two from each other. Now this is on a tiny little test case. Let's get some real data that we can try this on, and then let's do some performance comparison before we move on to the second part of the problem, because we haven't solved the whole thing yet. We need to find out, are they balanced or not. So for that, I'm going to copy in some functions from the defense workspace. We're not going to use these functions other than just their source as example data. So there's a turtle function, there's a Joy programming language interpreter, and then we need the comparison, the performance comparison as well. We copy those from defense. Right, and they are large functions, these turtle and joy, but not really large enough. So let's create some data. We have some data. I know that turtle has parentheses that are well balanced and joy has parentheses that are not well balanced. I looked that up before. So this gives us these two test cases. Let's call it yes and no on whether or not they are balanced. I'm going to take the source code of each one. So the vector representation of each, of turtle and joy, and then I'm going to make them a little bit bigger. So we're going to take that source code and reshape it using 100 times its current shape, and this gives us some large test data. We can see here that y is a bit over a million, and n is a couple of million. So now we can compare them, but instead of typing out the expressions with these three different functions, let's use an APL expression to generate the expressions that we are going to time. A little bit of meta programming here. So every function begins with a d. We concatenate that to each of these suffixes I, O, and F, and then we concatenate each of those to the entire argument y. So this gives us these three expressions, and we can run CMPX on those. And we can see that df, the one that is the fork, just compares it to one parenthesis and the other parenthesis and subtracting them, is by far the fastest one for these cases. What if we do it on something that isn't balanced? And again, interestingly enough, here di and do are approximately the same speed, but df still wins out. So this is the first part of the problem, determining when the parenthesis level changes, goes up and down. Next, we're going to use this to compute whether or not they're actually balanced or not. So we can use df, that was the fastest one, on our test case. That gives us these ones and zeros. And now we have to think about what does it mean that it's balanced. So there are really two things to it. One is that when the whole input is finished, when we reach the end, we have to reach down to parenthesis level 0. And when we go along, we're never allowed to dip below 0, because that would mean that we have closed more parentheses than we have opened. So we want the running total of the parenthesis depth. And that's very simple. We can do that with a scan. And this is then the parenthesis depth. And we also want to know what is the last element, whether or not it's 0. That would be the sum of them, and that's 0. So now we can just put together these two conditions. The first condition being that it is always true, it's true for all, that they are greater than or equal to 0 in the running sum. And also, it has to be true that 0 equals the full sum. Let's give this a name. We'll call it BA, because we're using this AND condition. Both this condition has to be true and this condition has to be true. But we can also do it a different way, a little bit more succinct, at least the first part. If we're saying it has to be all true, that's the AND reduction, that all of the elements have to be greater than or equal to 0. Now, the parenthesis level can only change by one step at a time. There's no double open parenthesis, there's only single open parenthesis, and they can only go down one level. So the first condition, which is to check that we never reach a negative level, it would have to pass -1 in order to become negative. It might continue further on, but it's a sufficient check to see whether or not we have any negative ones. So we can say -1 is a member of the running sum, means it's invalid. And a second, and then so now we're doing it in reverse. We're using a negative conditions, and similarly we have to say that 0 is different from the sum. So these are things that are not allowed to be present, and therefore, if neither of them is present, then our expression is well balanced. So instead of having an AND, we have to use a NOR. So we can call this balanced using NOR. Let's compare the performance of these two, and similarly we can create the expressions that we want. So we start off with BA and BN. We can just spell it out since there are only two of them. BN, and each one of them concatenated to the entire YD here. So we haven't assigned this yet. We should go up and assign this. So this is the depth for Y, and we should do the depth for N as well. And then we can get these two expressions and CMPX on that. And yeah, it's about the same. We can do the same thing for the nose. And that's a bit faster. And we can probably reason our way for that, because in BA we did a comparison of everything in the running sum, and then we checked whether they're all true. Whereas in BN we're not doing any comparisons we're not doing comparisons for all of the elements. We just start looking for -1, and as soon as we hit any -1, we're done. So the membership function will just terminate right there. It doesn't have to look through the entire array. So in some cases that can be faster. So here bn in some cases can be faster than ba. And that means we can potentially put together a whole solution here based on these. So we take df from before and we supply its results to bn, and that should give us the answer. And so we can do f on each of y and n should give 1 and 0, and that worked. We can also spell it out. But we'll come back to that because there's one more step we can do. Let's go back for a moment and think about what we're doing. The running sum and the full sum. You can then observe, since we're adding the elements from left to right, that means that the last element of the running sum is equal to the full sum. And so we're actually doing a little bit of unnecessary work. We're summing twice. Once we're summing a cumulative sum, and the other one we're summing everything again. So the last step of the cumulative sum is the same thing as doing the entire sum. It might drown in the mass of the cumulative sum, but still it could be a little bit of performance gain. So being that we found that bn was the fastest, let's rewrite that and so to say break out the scan and just pick out the right element from the scan, the cumulative sum, instead of using a new reduction. So let's break out the scan here, and we do that. Put the scan outside, and that means that this scan is already just the identity, but since we now have just a single argument with a dyadic function, we can just glue those together with the bind operator. And then we have 0 is different from, and this is the last element. So the last element of the scan, we can also just write that as a right reduction. So this is BNS. And now we can try to compare them. So we can say we're looking at Bn and BNS, each one concatenated to the YD. And we got a bit of a speed up there. And we can try it again with ND as well. And we got a bit of a speed up there again. So while it's not all about performance, this was fairly easy to go from one solution to another, and you got better and better performance. So we can put all of this together and a final solution. We define f, and then we take the definition from BNS here, and then we also want the parenthesis comparison, like this. This was the df. Now there's one problem. We want to apply this function, which is a fork, and then we want to apply this function, which is an a top. And this gives us, so to say, 3 parts. It would be a fork, and we would call this dyadically the scan. That's not what we want. But we can fix this by taking the scan and moving it to be in the top on top of the subtraction. And now we have a fork as the right part, where we have the 2 comparisons, and then the scan of the subtraction as the middle time. So the scan post-processes the result of the subtraction, and then we feed that over to where we extract the last element, so we can check that it's non-zero, and then we can and also we look whether or not there are any negative ones in that, and then we do the NOR at the end, and that is our solution. So this is a really good APL solution to the problem, and that's what I would use now that that's done, let's look at some alternative solutions that are not going to have good performance, but they're interesting to look at nonetheless. Something that would be near to many people, especially if they come from other programming languages, and especially if they come from Perl, is to use regular expressions. And we can do that as well. So let's go back to our test case here and observe it. We're only interested in the parenthesis. So we can do the set intersection with parenthesis just to get the structure. That's the only thing we're interested in. And now we can go in and remove pairs of parentheses. So here's a set of parentheses with nothing in them. Here's a set of parentheses with nothing in them. Here's another one. And then repeat the process until we are done. And if there's nothing left, that means that they've been balanced. If anything is left, any parenthesis is left hanging, whether it's opening at the end or closing at the beginning, then it's unbalanced. And that means if the result of this repeated transformation is the empty character vector, that means it's balanced. Okay, how can we define this? So we start off by applying the function of intersection with the parenthesis, and then we can write a regular expression. Now we have to escape the parenthesis and replace with nothing. So we can apply this on our test case, and then we can see it removed the first parenthesis and the last parenthesis and the inner of the middle parenthesis. And then we just need to do it again and check whether or not it is the empty character vector. But we don't know how many times we're going to do it. Therefore, we have to say that we are doing it until nothing more changes, also known as power match. So we're applying it until there are no more changes, and that allows us to do it. We can try this, but it's probably a bit much to do it on the large case. Well, we can try it. Oh, that worked. Okay, and we can do it on the large case of the no as well, and you can see that that worked. So let's call this regular expressions. We can just put it up here. That's our regular expression solution. This is not going to be performant for APL, but well, oh, I'm missing a red argument. That is because, oh yeah, of course, this is because this is a monadic function we want to apply to our argument, and this is a monadic function we want to apply to our argument. We need to glue them together to become a top. Right there. But regular expressions are very expensive. We have to spin up the entire regular expression engine and possibly transform our input to a format it can understand and get the result back, collecting information, extract information from there. We can actually use quad R. It's a fairly new feature that was added, to use quad R for replacements of plain text from this character vector to this character vector as well. And we do that by applying the variant operator, where we switch regex off. And now we don't need to escape the parentheses anymore, because now it's just plain text replace from these two parentheses to nothing. So let's call this, well, it's not really regular expressions anymore, it's replace, but well, no regex, I guess. However, keeping this method in mind, we can also try implementing it in APL, and that might give even better performance. So now we have to think a bit. We have to find places where we have an open paren and close paren, and then remove those. Well, let's look at our test case. We can easily use the find function to find a we need to remove the all the characters that are not parentheses first. So let's take this and compare with this. We can see how it matches every place where we find open paren, close paren, we get a 1 bit indicating so. However, our problem is that we want to find to remove those parts. So we need to indicate also where the closing parenthesis, corresponding closing parenthesis is. Let's space this out a little bit for readability. And what we can do here is we can do a rotate. So we can do both this mask that we just computed, or when it's rotated one step. And this indicates both the opening paren and the closing paren. But we don't actually want to preserve those, we want to get rid of those. The way we do that is just by flipping the OR to an OR. And this gives us a mask indicating just the characters that we want to keep. So now we can say we want this, just the text that has the characters from open paren, close paren, and then we glue this together. So we have a function here, and then -1, and that puts it all together, and then we can filter it using that. So that gives us this. Now it's not useful to look at the original anymore. And then we just need to repeat this process over and over. But we don't need to repeat removing the everything that's not parenthesis. We just need to repeat this squeezing of away open paren, close paren. So we can do the same thing with power match again, and then we can compare to the empty character vector like that. So we can put all of this together. Here we've got, we can actually put it as a top and glue this together again. And this is using find. So we can try find on each of y and n, and it gives us 1 and 0. So now we basically implemented the same transformation that we used regular expressions, and then the quad r just for text replacement, and we've now implemented that same transformation in raw APL. We can do a comparison of the performance of these. So we have RE and RE0 and FI, and we're comparing them to Y. So, and we can see that the regular expression engine is very heavy weight. It's much faster to do it either with replace without regex or implementing it ourselves. And we can do it on n as well. And a similar thing. So it's probably easiest to implement it just with the text replacement that's built in. But if you implement it yourself, you can get a little bit more performance right there. And finally, some kind of joke solutions. We can kind of circumvent the problem, because this kind of parenthesis matching is already happening in mathematics, in most programming languages as well. When APL evaluates an expression, it has to do this kind of thing as well. Such an expression as this can of course be evaluated as APL. If our parentheses don't match, then APL will tell us that there's unpaired parentheses. That means the APL interpreter itself somehow has this same functionality built in, and we can leverage that. The same thing happens if we use braces that are not in defense, that are not paired up correctly. Then APL will tell that they're unpaired braces. Let's see how we can abuse this. We can start off using the braces and doing the same mapping as we did way in the beginning, mapping to 1, -1, and 0. And here we'll map the input to braces instead. So we look up in open and close parentheses, and then we use that to index into open and close brace and a blank. So this gives us an expression which doesn't do anything useful. It won't be able to actually run, but APL's parser will protest if it doesn't look right. in order to force APL to actually use this function, we have to execute it, and that returns a function with a strange display form. That's not very interesting. The only thing we want to see is whether or not this errors or not. Now, if it does error, then we can catch that error. If it doesn't error, we need to apply this function in a way that won't error. And how can we apply a function that's completely meaningless and doesn't do anything? It will just result in a value error. Well, we can take this function and use it to reduce over a scalar or one element vector. Now, reducing over a scalar doesn't change that scalar at all. So APL will never actually use the function. It just registers that it's there and will error if the function doesn't work. So this should work fine. And if we try to do it with an expression that doesn't work, like what we did before, then we should get an error. So the only thing that's left here is to transform this into a function. We wrap it in a defin, put in an error guard. If we get any error, then it's not balanced, and otherwise it's going to reduce over the 1, and reducing 1 doesn't change the 1, so that's the one that we want for a result. So this uses nesting depth of defins. We can try this, but I think we'll run into a problem that the test case is just too big for the parser to deal with. Yeah, this isn't working. Why isn't this working? Giving the wrong result. Oh, yeah, of course. I know why it's not working. Because the test cases are in fact too big. So let's just try it on the vector representation of turtle and joy. Okay, now it's working. The reason it's giving it a 0 is because the error guard is catching the error condition that the expression is too complex for APL to parse. So this is working. And here's another approach using stranding of parentheses. So let's say we take we start off the same way by extracting just our parentheses, and then we concatenate a 1 in front of each character, and we also concatenate a 1 in front of everything, just in case the expression is empty. And now we should be able to run this. We can execute this in APL. It gives some nested array. But this will force APL to check whether the parenthesis level is working. So we just need we can format it to flatten it, and then we can try executing it, and then we just need to see whether or not that will work. So if we hit any error, return a 0. Otherwise, we ask for the first element of this, which is of course going to be 1, because we should maybe flatten it as well, just in case it's nested. Because it's all 1s everywhere, and this is using nesting depth of parentheses to parse this, and we can try it. And what we had before. So this is for joy, and it's okay, and for turtle. Oh, this is not right. This is not working. So see here. Oh, of course we put a T here instead of putting an omega. Well, silly me. Okay, turtle and joy. Yeah, so those we give the correct result. And of course the performance of this is going to absolutely horrid. I'm not going to bother you with this, but these are just some fun solutions of abusing the system. Thank you very much for watching.